Okay, let's dive into a genuine mystery, one that sits right at the heart of modern physics. It's a story about, well, our most successful theory of reality and the absolutely shocking mathematical paradox it's built on.
So first things first, let's talk about quantum field theory, or QFT. This thing is an absolute triumph. It predicted particles like the positron and the Higgs boson decades before we ever found them. And its predictions, the numbers it spits out, like the magnetic moment of the electron, they match what we measure in experiments with an almost unbelievable precision. It's a victorious theory, no doubt about it.
But here's the twist. If you dig deep into the math, into the very foundations of QFT, you find a result that points to what a physicist would call a seeming absurdity. It basically says that this unbelievably successful theory is technically incapable of describing the one thing it's famous for, particles interacting with each other.
So, Section 1, a victorious, absurd theory. How on earth can a theory be both of those things at the same time? To get our heads around this, you have to understand something really fundamental about quantum mechanics. There isn't just one single way to describe how things change over time. Physicists actually use different mathematical frameworks or pictures to describe the very same reality. Which brings us to our next section, 3 pictures of reality. And yeah, we're going to have to get to know all 3 of them, the Schrödinger, Heisenberg, and interaction pictures. Now, this might sound complicated, but it's actually pretty intuitive. Think about it like this. How do you describe a sunrise? You could say the Earth is rotating, and that rotation brings the sun into view. That's one picture. Or, from your perspective, standing on the ground, you could just as easily say the sun is moving across a fixed sky. That's another picture. Both of them perfectly describe the same event, and they both tell you when it's going to get light. Well, quantum pictures are kind of like that, just different mathematical ways of looking at the same physics. So let's break them down real quick. In the Schrödinger picture, you imagine the quantum state itself changing over time, while the things you measure stay fixed. In the Heisenberg picture, it's the total opposite. The state is frozen, and the measurement tools, the operators, are the things that evolve. And then you have the interaction picture. This one's a clever hybrid of both, where the state and the operators kind of share the work. In this hybrid, this is the key to our whole mystery. All right, let's talk about the indispensable interaction picture, because oh boy, is it ever indispensable. So what is it really? Well, it's basically a brilliant problem-solving strategy. See, real-world particle interactions are unbelievably complicated to calculate. So what physicists do is they split the problem in 2. You have a simple part they already know how to solve, that's the free theory, and then you have the messy interaction part, which is what they're actually trying to figure out. And here's the genius of it. You take a really complex system, and you basically load all the simple, easy-to-solve evolution onto the operators. That leaves the quantum state to change only because of the messy, complex interaction. It just makes the math workable, and it lets physicists calculate the effects of forces piece by piece. And listen, don't make any mistake about it. This picture is the absolute engine of QFT. It's the foundation for pretty much every calculation involving particle interactions, from what happens inside a particle collider to how electrons behave inside a new material. It's the tool that makes QFT the predictive powerhouse that it is. And this brings us to a mathematical physicist named Rudolf Haag. Back in the 1950s, he took a really hard look at the mathematical foundations of this picture, and he came to a pretty devastating conclusion. And there it is. That's the core of Haag's theorem. When you apply the full mathematical rigor, when you're really careful about relativity and quantum mechanics, it proves that the interaction picture doesn't actually exist. The only way the math holds together is if the theory is trivial. And trivial is just a fancy word for no interactions at all. So, you see the paradox, right? How can physics completely rely on a mathematical tool that, strictly speaking, is a fiction? Is the entire magnificent building of quantum field theory, with all its mind-blowing predictive success, built on a mathematical house of cards?
Well, physicists are a pragmatic bunch. The theory works so well that they've found ways to live with this paradox. They've figured out why it happens, and more importantly, how to get around it.
The problem, as it so often is in physics, turns out to be infinity. See, Haag's theorem kicks in when you consider a universe that's infinite in size, with infinite possibilities. In that kind of universe, the world of free particles and the world of interacting particles become so fundamentally different that there's no mathematical bridge to connect them. They are, for all intents and purposes, in 2 totally separate mathematical universes. So how do they actually get away with using it? Well, they've got a few clever tricks. First, they put the theory in a finite box. All real-world calculations basically assume the universe is finite, and in a finite box, Haag's theorem just doesn't apply. Second, pure pragmatism. At the end of the day, these methods give us the most precise predictions in all of science, so the foundational weirdness is often just ignored. And finally, they use a powerful bag of tricks called renormalization. It's a super sophisticated way to sweep all the problematic infinities under the rug, which cleverly sidesteps the theorem's main problem. So really, this helps us understand what QFT is. It's like this gigantic, incredibly intricate jigsaw puzzle. Huge sections of it are perfectly locked together, and they give us this absolutely stunning picture of reality. But some of the pieces that connect those big sections, pieces like the interaction picture, they're kind of just tenuously locked in. They hold the whole puzzle together, and they let it work, even if nobody's 100% sure why they fit so well.
And that just leaves us with this one fascinating final thought. Haag's theorem proves that our best, most successful theory of the universe works despite having a deep mathematical inconsistency baked right into its core. It really makes you wonder, doesn't it? What other victorious absurdities are we relying on right now? What other paradoxes are hiding in plain sight, just holding up our entire understanding of reality?